Welcome to the Shape of Space Tensors. This is the first of two lessons on tensors. There's two ways of approaching tensors or describing them. One is the multilinear transformation approach, which I'll cover in this slide set. And then there's a second approach, multidimensional arrays, which I'll cover in the second lesson. In this lesson, we're going to develop the concept of a tensor as a multilinear map. A tensor is more than just a multilinear map. It actually has another property concerning change of basis that I'll get to. I'm assuming that the listener is familiar with multilinear maps and dual spaces. And if you're not, I'll give you a link to a video that I've done on those topics. The lesson follows along the lines of a chapter from a book, or at least part of a chapter from a book. This book here, let me point to it. I believe it's chapter 11. And the book is freely downloadable from the Internet Archive. And I'll give you all the information on that and the links to this video. So let's get started. Let V be a finite dimensional vector space over a field. We're going to confine ourselves to the field of real numbers. Let VR be the R-fold Cartesian product. So we have R appearances of V here. Further, let T be a multilinear mapping from VR to R. Such a mapping is known as an R tensor on V. There's a few other names for it, but we'll go with the term R tensor. The set of all R tensors is denoted by T, script T sub V, R of V. So of course V is the vector space and R is the number of appearances of the vector space in our Cartesian product. We define addition and multiplication as follows. S plus T, where S and T are these multilinear maps or R tensors. Applied to a vector is just S applied to the vector plus T applied to the vector. Then the scalar times T is just apply T to the vector and then multiply by the scalar. So these are definitions. And with these definitions, the set of all tensors over this Cartesian product are a vector space. So it's actually a dual space of this vector space here, this Cartesian product. We can extend the above definition, this is what's typically done, to get a more general concept of a tensor by including support for dual spaces. So rather than just taking the tensor going from the Cartesian product of V to R, we now can add in a Cartesian product of a number of dual spaces, and you get this expression here. So in green is what I've added to the definition from the previous slide, and as I stated, V star is the dual space of V. V star is repeated S times, and V is repeated R times. The number of instances R of V is known as the covariant order, and the number of instances S of V star, the dual space of V, is known as the contravariant order of T. A tensor of covariant order R and contravariant order S is said to be of type RS. The set of all tensors of type RS is denoted by this here. So we kept the R in the subscript as we had before, and then we put the S here for the number of these dual spaces up top. And we still have the operations as defined in the previous slide. So this thing here, all these mappings, is a vector space over R. Then we have some special types of tensors. A tensor of type 0, 0 is defined as a scalar, so you don't have any vector spaces here. So that's just a scalar. A tensor of type 0, 1 So in other words, you'd have your R is 0, so you'd have 0 of these, and 1 of the dual space is known as a contravariant vector, and a tensor of type 1, 0, so here you would have R being 1, so you'd have just a vector V, vector space V mapped to R. That's known as a covariant vector, or just the con vector. In what follows, basis vectors for V will be indicated with a subscript, so E sub I, and basis vectors for V star, the dual of V, will be indicated with a superscript, omega J. In addition, this notation here will be written without the V, since we're only going to be talking about typically one vector space at a time, which I'll mention somewhere in my slide on the particular topic, and the field R is also understood. Okay, so keep that in mind. This assumes a V and some vector space V and a mapping to the real numbers. There's a lot of notation on this slide, but the concept is relatively straightforward. What I want to do is take any set of vectors from the domain of the tensor in this tensor space, and then show how it gets mapped in terms of the basis for the vector space V and its dual V star. And that's what I have here. And I'll go through the details in a moment, but that's the idea, is to take an element from the domain and show how to write it in terms of some coefficients times the tensor evaluated across the basis elements. So these L1, L2 up to LS ranges from 1 to n, since the basis has n elements in it, and the same for these here. And then this thing is known as I should say, because these are over many different values. These are known as the components of T, and it's written in this notation here. Okay, so let's go through this in detail. We take any element in our tensor space, so it has R instances of the vector space V and S instances of the dual of V. And then we have E1 to En is the basis for V, and since the vector space and its dual are isomorphic, you have the same number of vectors in the basis for V star. And then what we do is generally represent an element from the domain of this tensor. So we need to take R vectors, U1, U2 up to UR, and S vectors from the dual, and then we write each one of those vectors in terms of their basis. So we write each one of the vectors U1, U2 up to UR in terms of the basis for V, and that's what's here. And take note that that's Einstein notation, so it's really a linear combination. It's over the sum J equals 1 to n, since there's n vectors at the basis. And then since we used superscripts as the indices for the basis for the dual, we have the summation slightly different from up here. You notice the summation is superscript, subscript, again using Einstein notation. So we have one such representation for each vector Vk from k equals 1 to s. And so basically what I've shown up here is representing all of these vectors in terms of either the basis for V or the basis for V star. And then I've just plugged in V1 here, V2 up to Vs, and then did the same thing for the different u's, u sub 1, u sub 2, all the way up to u sub r. We have this. These are summations in here. Each one of these, for example, the 1 over L1 goes from 1 to n. Same thing here, and all the way down. Then from the, and I put them in the, I put the coefficients in green. So these are just scalars. The things in green are just scalars. From the multilinear property of t, you can pull all these out, which I've done here. So this is just the product of a bunch of scalars. And then what you have left is just the tensor t evaluated at these particular basis elements. And again, the Einstein notation applies here, summation here, here, all the ones in between. Same thing for the elements from V, the U1, the UR. So these are all summations. And then when you move the coefficients out, you still have the summations remaining. So you have a summation here over L1, L2, Ls, and so on. So yeah, as I just said, the Einstein notation or convention applies to both lines here. There are R plus S sets of indices, each summed over n. The L1, L2, J1, so forth, they all have n possibilities. And so you get leading to n to the R plus S terms in the summations. And you can see the advantage of using the Einstein notation here. We would have just had a whole bunch of summation signs, both inside here and then outside here. And I could see where Einstein would have favored having this simpler notation, which he recognized is, being an advantage in terms of writing things out. So as I mentioned when I started this, these terms here, these guys here, are known as the components of t. So there's a lot of them. There's r to the n to the r plus s of these, because L1 ranges from 1 to n, L2 ranges from 1 to n. Each one of these can, the superscript or subscript can range from 1 to n, and you have r of these and s of these. So there's a whole bunch of these components. But the idea is that if you take any element from the domain, you can always write it using this one of these components, or a collection, some of these components, I should say, and they remain the same. You compute those once and they remain the same. What varies are the scalars you need to represent your u's and v's in terms of the basis elements. And then this is a shorthand notation for these. All right, so let's look at an example. There's an awful lot here, and the notation, I agree, is kind of nasty. And it took me several attempts to finally get my hands around this. So it's not an easy, at least in my opinion, understanding tensor notation is not an easy thing to do. And hopefully this video will help you a little bit in getting there. Let's look at an example of a tensor, T33. So in other words, 3 instances of the vector space and 3 instances of the dual of that vector space. But we're not actually given the vector space. We're just told it's of dimension 3. And then we're given this formula for the components. So there's no Einstein notation implied here. This is just 3 Kronecker deltas multiplied times each other, and then 2 Levi-Civita symbols multiplied together. So it's a fairly simple formula, but it's specifying the entire tensor space. We can look at a few examples here. Here we have taking the values 1, 2, 3, 1, 2, 3. We plug that in for I, J, K, L, M, N. So this is 1, 1, 1. And if you recall, 1, 2, 3 is an even permutation, so the Levi Civita symbol would be 1 in that case, so 1 times 1, we get 2. Then we can take 1, 1, 2, and the Kronecker deltas are 1, 1, and 1, so we get a 1 here. But this is not a permutation because you have the 1 is repeated. For a permutation, the numbers have to be different. So you have a repeat here. So the Levi Civita symbol is 0 in that case. And so you add that to the 1, you just get 1. Then we have one last case. These numbers don't have to be the same. So here's an example where they're not. You have 2, 1, 3, 1, 2, 3. So let's see, this is 0, and that's 1. So this term is 0. And then the 2, 1, 3 is odd. So the mapping would be to -1. And then this is even, so we get 1. We get -1 for the product. So the total number of all of these components is n to the r plus s, where n is the dimension of our vector space, that's 3, and then r and s are these two numbers here, 3 and 3. So we get 3 to the 6th, which gives us 729 components. So we're not going to compute them all, but we have this formula that we can compute any one that we need to. We can reduce the number by looking at subtensors. For example, we could take I and L equals 1, and then that would have a smaller number. We would still have n equals 3, but then R and S effectively, since we've set two of them to constants, would just be 2 plus 2, so we'd get 3 to the 4th possible components. Now, the interesting thing is, given this, we can compute any mapping of the tensor from the 3 instances of V and 3 instances of the dual space and to the real numbers, and I'll show you that in the next couple of slides. On this slide and the next, I want to further analyze the tensor space we defined on the previous slide in terms of its components. I wrote that formula down here. So to that end, let's assume that V is actually the three-dimensional Euclidean space. And let's take 3 vectors from R3 and 3 vectors from the dual of R3. And then we want to apply our tensor to and these are arbitrary vectors. So we want to apply our tensor to these 6 vectors and prove that it equals this formula here, given this. And the way we prove that is we use this formula that we derived earlier. We write each one of these vectors in terms of their basis elements for V, and then the dual of V, and then we apply the components to it. So let's go about doing it. We're going to do it in 2 pieces. So first we'll apply this part of it, the component, to our vectors, and then we'll apply this on the second slide. We'll apply this, and then we'll put it all together to get this formula here. Okay, so these are our components, or coefficients, I should say, for our 6 vectors. So for example, this one here is corresponds to the first vector, and it would be V1, and then L is the index for the different components of V1. Remember, each one of these has 3 components because they're in R3 or the dual, so that's what the L is. And then the V2 is the second vector, and the M stands for the different components. Again, we're just following this formula here, but again, we have something simpler. We just have 6 vectors to deal with. All right, then we just continue for the V3, and then for the 3 vectors, U1, U2, excuse me, UI, UJ, and U1, U2, and U3, I should have said. And then the indices are up here in the as superscripts. Okay, so this equals this. Remember, these are just all scalars since we're taking one component at a time. So I put the U1 was V1, the V2 was U2, and V3 was U3. So this equals this. Then we apply this to this here. And since there's no M or J in these first two here, I can move this here, which I've done in this line here. And then since there's no N or K until you get all the way here, I can move this Kronecker delta all the way to the end. Then we have these 3 things. Then we do a summation over I using the Einstein notation. So this is going to equal 0 other than when I equals L. You get this here, U1L. We didn't touch this yet. Same thing here, when J equals M, this is the only time you don't have a 0 term, and so you get U to M and then V to M. Same thing here. Then we apply the Einstein summation again over the L this time, and again, it'll only be non-zero when L is 1. This is only non-zero when M is 2, and this is non-zero only when N is 3. And so we get this, and that's our first term in the equation that we want to prove. Then the next step is we want to apply these, the product of these 2 Levi-Civita symbols times our coefficients for our 6 vectors. And we do that on the next slide. So let's finish this off. Just to recall, we applied the first part of this formula to our vectors, our components of our vectors, and we got this. Now we want to apply the second part of this to our vectors. And that's if you recall, the second part of that is the product of the Levi-Civita symbols. So that's what I'm doing here. I applied this to the U's, and this is from our theorem 78 from I believe it was the last lecture I did. It equals this. We've proven this before, and you could write this in sort of a shorthand notation this way here, and then you apply the other Levi-Civita symbol to the V's, and you get this, and this is a shorthand way of writing this here. It's just saying this is the first row, this is the second row of your determinant, this is the third row. Same thing for this. And so we get this product, and that gives us the product of the 2 determinants, and so that gives us our formula. So it's kind of interesting. The output scalar depends on the input vectors, but the tensor components, this thing here that we were given, is fixed. Once you know the basis for V and the dual of V, this thing remains the same, and then you can evaluate different sets of vectors, and given this formula for the components, you just need to compute this here. Okay, so that's our example. Not all that easy. It took 3 slides, but it may seem easy compared to the theorem and proof I'm going to do next. The set script T SR of tensors of type RS over vector space V, which is of dimension n, forms a vector space of dimension n to the r plus s power. We sometimes call this a tensor space, just to emphasize that its elements are tensors. So in order to prove this, we need to find a set of tensors which will then prove are a basis for this set. So to that end, for each set of indices corresponding to R and S here, such that each index is between 1 and n, that's because the dimension of V is n, define the tensor shown here, an element of our set, such that its values on the bases e sub I for V and omega superscript k for the dual of V are given by this equation here. So it's just saying applying this tensor to these basis vectors is a product of Kronecker deltas, so a pretty simple output. It's clearly a real number. It's either 0 or 1. So that's our set. We want to show that these tensors form a basis for TSR. So next step is we'll take an arbitrary vector, or a set of vectors, R from V, and S vectors from the dual of V. Then using Einstein notation, we'll represent how each one of these vectors is written in terms of their associated basis. So the U's are written this way here, basis element and then the coefficient, or the component. So where Aij is a real number is the jth component of Ui. And then for V superscript k, we can write that as the basis vector times the coefficient or component. And this BLK is a real number, and it's the lth component of VK. Okay, then what we'll do next on the following slide is we'll take our tensor and evaluate it over this set of arbitrary vectors. I copied our equation, or definition actually, for our set of tensors, which we want to prove to be a basis. Copied that up here. So, as I mentioned on the last slide, we want to take our tensor and then evaluate it over this arbitrary collection of vectors from V and the dual of V. So we have this here. Then, as you recall on the last slide, we defined each one of these in terms of the basis vectors for V and the dual of V. So I just plugged that in here. So that's what I did in going from here to here. Then we use the multilinear property, and we can factor out all the coefficients. See that here? And then it's just our tensor evaluated at the basis vectors, but we've defined what that is, so we can plug that into here. And then we can match these up, so let's look at a few of them. If you take this first one and this first Kronecker delta, the only time this product here is not 0 is when L sub 1 equals K sub 1, and then this is 1, and this becomes B sub K sub 1, 1. We can do that for all the other B's here, and maybe we'll just look at one of the A's. So if we take this and the this one here, this and this, then you sum that over J sub 1, and the only time that's not 0 is when J sub 1 equals I sub 1, and you get this term here, and then the same for the other A's. Okay, so our tensor evaluated at this arbitrary set of vectors is this here, which is just really the coefficients when you represent these vectors in terms of the basis vectors. Yeah, so what we're left with is we need to show that this set of tensors is both linearly independent, which I'll do on the next slide, and also spans our tensor space. To show linear independence of these tensors from our set S, we'll take a linear combination and set it equal to the 0 tensor, and then prove that these coefficients have to be equal to 0. To do that, we'll take a sequence of basis vectors from the the dual of v and v, this here, and we'll apply both sides of this equation to this set. Now, when we apply the zero tensor to this sequence, we're going to get 0. And then when we apply the left-hand side to this, we'll make use of the definition of the vectors, the tensors, S. So this, as you recall from the 2 slides ago, is equal to the product of these Kronecker deltas. And then when you do the Einstein summation over this, you just get the coefficients. And as I mentioned, evaluating on the other side of this, we get 0. Now, any element from the domain of our tensor can be written in terms of these basis vectors with some coefficients, but the coefficients just factor out in terms of the multilinearity property, and so you're going to get 0 no matter what what sequence of vectors you evaluate this on. You're going to get this. You're going to get these coefficients equal to 0. So that's the generality of this statement. And then once we've shown this is equal to 0 in every case for all these different choices of indices, then that means that any linear combination of these tensor vectors equal to 0 implies that all the coefficients equal 0, and that means they're linearly independent. Okay, so we have one more thing to prove. We need to show this is a spanning set for our tensor space. We'll do that on the next slide. The last part of our theorem involves showing that this set spans our tensor space. And to do that, we'll consider this product here, which is effectively a linear combination of the tensors from S based on some arbitrary tensor T, this thing here. And we're going to show that this product and T yield the same result when applied to an R plus S tuple consisting of basis vectors from the dual of V and the vector space V. So by definition of tensor components, we have this. Then looking at the product applied to this R plus S tuple, this part here, S times applied to the R plus S tuple, as we defined earlier, or showed earlier, is just the product of these Kronecker deltas. And then we apply T to this, and that's an Einstein summation, and we get this result. And so we've shown that T and this product here are the same. And so any element from our tensor space can be represented as a linear combination of vectors, tensors from our set here. And that's what we wanted to show. Okay, so this set is both linearly independent, and as well as a spanning set of our tensor space, and therefore it's a basis. It's possible to write a basis for our tensor space TSR in terms of the bases for V and the dual of V, and I'll show you that a little bit later in this lesson. But in order to build up to that, we need to define something known as a tensor product. So we take two tensors, S and T, from our tensor space, and then we take these sets of vectors. You notice we have R sub 1 of these and then R sub 2 of these with V, and you'll see why I'm dividing it up like that. And then we have a set from the dual, and again we have S sub 1 of the alphas and S sub 2 of the betas. The following product is linear in each of the R sub 1 plus S sub 1 plus R sub 2 plus S sub 2 variables, this thing here. And we define what's called the tensor product, which is an element of this larger tensor space, as follows. The tensor product of S with T acts on all of these elements. You notice they're coming from both of these arguments, and it equals this product here, one tensor times another. Remember, these are both the outputs of both of these are just real numbers. Okay, so that's called the tensor product. This is not the Kronecker product. It's different, but unfortunately, the same symbol is used commonly, so we need to be careful of that. I want to state some laws concerning the tensor product. We have an associative law here in group R and S, and then take the tensor product with T, or we can group S and T, and then take the tensor product with R. We have two different distributive laws. And then we have this law here that allows us to take the scalar and move it from S to T like this here, or move it out altogether. However, the tensor product is not commutative. And as I mentioned on the previous slide, this symbol unfortunately is used for both Kronecker product and tensor product. In the event that the two cannot be distinguished by context, we will use this notation here for the Kronecker product. But I don't think I ran into this issue, but in any event, I'll mention it here. So this is the theorem I alluded to a few slides previous. If V has a basis, E1 to En, and the dual of V has corresponding basis omega 1 up to omega n, then a basis for the tensor space is given by this collection, this set here. And these are, in fact, tensor products. That's why we needed to take that sidestep and do some definitions of the tensor product before we could get to this theorem here. And then all these indices, the j's and the i's, they all range between 1 and n inclusive. And the dimension of this tensor space is n to the r plus s. I'm not going to give you a proof here, but I'll give you a couple of references. One is in this book by Errata and Williamson, and there's another proof by Lee, and it's a corollary 12.12, and I'll give you the references to these. I believe both of them are available online, so if you're interested in the proof, you can look that up. In what follows on this slide, we'll derive the change of basis formula for a tensor. Let T be an RS type tensor over a vector space V, and E sub I be the original basis, and then the E superscript I represent the dual basis. And the relationship between the original basis for V and the original basis for the dual is given by this. We can always select bases such that this formula holds. That's a formula related to dual bases. And then let these symbols here represent the new bases for V and V star. The change of basis are given by these formulas here. So this is the change of basis for V. This is the change of basis matrix. And then this is the change of basis formula for the dual. And it's just the inverse of this change of basis matrix. The components of T with respect to the original basis are given by definition by this. We defined that at the beginning of this lesson. And we want to find out what the change of basis component, we want to find out what the components are for T under the change of basis. So we'll compute that. This is the definition. Then I needed to change the indices a bit, but I'm using these formulas here. Just plug that in. Then the multilinearity property of tensor allows us to pull out the coefficients, and then it's times. I couldn't fit it on one line, it's times just the t evaluated at the original basis vectors, and then we get this formula here. I'm just plugging in this over here. Okay, so this is the representation of the components for the tensor under the change of basis. This is important because a multidimensional array needs to follow this formula in order to be considered a tensor. In fact, this is the defining property of a tensor in addition to the multilinearity property. What we'll see in the next lesson is the multidimensional array definition of a tensor. And that does not require this additional change of basis property that we've shown here. And in fact, the next lesson will be much simpler because we don't have this requirement.